Good morning. The presentation will focus on the technical foundation of our project and how we implemented the analysis. Our project analyzed the food price inflation across Canada from 2017 to 2025, used statistical model and machine learning technology to understand historical inflation trends and to forecast price for 2026 to 2028. Technically, the core objective was to build a clean, reliable machine learning pipeline capable of analyzing the historical CPI data, comparing multiple forecasting models, and gathering accurate predictions. We framed this using four research questions. Which model performs best for inflation forecast? How have food prices changed across provinces over time? Third, can we predict future inflation with confidence? Fourth, are there any province-specific inflation spikes we can detect programmatically? Upcoming is what the data set that we use and the processes. So our data sets come from Statistic Canada. The entire analysis was built in Python. We used pandas and NumPy for data cleaning, Seaborn and Matplotlib for our visualization, Sklearn, XGBoost, and Transpo for model development. These libraries give us control over the entire workflow from pre-processing to hyperparameter turning to forecasting. These are the code we use to import the required libraries. The screenshots. This is the number of rows and columns and the name of columns. Let me walk you through our technical workflow. So first, we begin by importing all the required libraries. Then we load the CSV file. We clean the dataset by forward filling missing values, removing duplicates, normalizing CPI, and engineering time-based variables like year and month. Next, we calculated the month-over-month inflation rate using Python formulas. We also created rolling average, cumulative indexes, and applied standard scalar to normalize the training data for our ML model. We generated visualization using Seaborn, line plot, heat maps, and trend curves to check patterns and potential seasonality. Our modeling pipeline tested three approaches: linear regression as baseline, XGBoost for advanced embezzling learn, and LSTM for deeper learning sequence forecast. We applied train test split, scaled the feature with the models, and evaluate them using R-square, RMSE, and MAE matrix. After comparing all the metrics, linear regression emerges as the most stable. We then use it to forecast inflation for 2026 to 2028, producing both numerical results and visualization outputs. You'll see further.
Thanks, Anya. So, hello everyone. I am Akhil. To start, we focused on data cleaning and transformation because accurate forecasting depends on a reliable dataset. We first examined the dataset for inconsistencies. Any missing values were handled using a combination of forward fill and mean replacement, depending on the nature of the gap. We also checked for and removed duplicates to avoid distorted trends. So, as you can see in the code, next we normalized the CPI values, which helped us bring all provinces onto a comparable scale. We also extracted the year from the monthly timestamps and computed annual averages for each province, making it easier to analyze long term inflation patterns. By the end of this step, the dataset was clean, structured, and ready for deeper analysis. So, moving forward to the next step, which was feature engineering. Here's the screenshot of the code. Next step is feature engineering, where we generated new variables that help the models detect patterns. The most important engineered feature was inflation rate, calculated using the standard CPI formula shown on the slide. We also created rolling averages, which smoothed month to month fluctuations, and a cumulative index to show all overall rise in food prices over several years. Since our models require numeric inputs, we applied province encoding and then scaled all features using standard scaler to ensure uniformity across inputs. These engineered features significantly improved the model's ability to learn inflation behaviors. Here is the code for that and some of the visuals. And here's the screenshot. We then moved to exploratory visualization, which helped us understand the data intuitively before modeling. Using Seaborn and Metaplot library, we plotted various charts showing CPI movements and inflation patterns across provinces. These visualizations allowed us to see clear spikes, especially around 2021 to 2023, and identify provinces that consistently show higher or more volatile inflation. This step gave us our first insights into regional differences and long term trends. Here's the code for that and the screenshot. So, moving to the next slide, to validate our findings, we performed a detailed statistical analysis. We begin with descriptive statistics, finding a mean inflation rate of approximately 2.9% with a standard deviation of 1.4%. We ran normality checks using histograms and QQ plots, which helped us assess the distribution shape. Next, we performed the ADF test, which confirmed that the series is non-stationary, meaning that trends have to be accounted for during model development. Finally, we checked multicollinearity using VIF scores, and all values were below 2, confirming that our features were independent and reliable for modeling. Overall, this statistical validation ensured our model inputs were accurate and meaningful. So, thank you. I'll hand over to Josna for further presentation.
Model development and evaluation. We developed three models, each chosen for specific technical reason and to test different hypotheses about how inflation behaves. Our first model is linear regression, our baseline model. We choose it because inflation generally moves in a predictable and cumulative pattern. A simple trend can often explain a large portion of its variation. When we trained this model, we achieved R square of 0.908, RMSE of 0.0479, and MAE of 0.0464. The residual plot shows no systematic error pattern, confirming that the model fit the data well. Linear regression turned out to be both accurate and interpretable, a major advantage for policy analysis where decision makers need clear explanation rather than just black box prediction. The second, the second model was XGBoost regressor, chosen because it captures non-linear relationships and interaction between provinces and time. We tuned parameters like learning rate, maximum depth, and number of estimators. The model achieved R-square of 1, indicating a perfect training fit. But we recognize this is as a slightly off-fitting. Still, it relieved that inflation patterns were strongly determined by time variable. There wasn't much randomness left unexplained. The feature importance chart confirmed that year and province were the dominant predictors, reinforcing our EDA insights. The third model was LSTM, long short-term memory neural network, designed to test whether inflation rate depends on sequential pattern. Essentially, whether the system remembers previous years. We used two stacked LSTM layers with 64 and 32 neurons, a dropout rate of 0.15, and ADAPT optimizer with a learning rate of 0.003. However, since the dataset contained only 8 years of annual data per province, the sequential length was too short for deep learning. The model was unperformed with R-square of 0.3865, RMSE of 7.66, and MAE of 6.32. While not accurate, this result was still informative. It shows Canada's inflation is structural and gradual. So simple models can often predict effectively. When three models compared, linear regression emerged as the best balanced model, high accuracy, low error, and strongly interpretable. Estibute was highly accurate but less generalizable. And LSTM showed the limitation of applying deep learning to small and yet yearly dataset. We use three evaluation metrics, R-square, RSME, and MAE because together they measure how much variance the model explains, how large the average errors are, how consistent the predictions remains across test samples. Linear regression performed well on all three, confirming it as the optimal forecasting choice for.
Thank you, Sania. In this phase, we tested three predictive models: linear regression, XGBoost, and LSTM. Linear regression provided the best balance between interpretability and accuracy. XGBoost achieved the highest accuracy but showed signs of overfitting. The LSTM model required more time series data for stronger performance. Based on evolution metrics, we finalized linear regression as our primary model due to its stability and consistent results across provinces. This slide shows the model evolution. On the left, you can see the code used to calculate R square, RMSE, and MAE. The bar chart compares all three models. Linear regression shows the lowest error, XGBoost is slightly higher, and LSTM performs the worst. This confirms linear regression is the most stable. Here are the main insights from 2017 to 2025. Food CPI rose about 40%. The average basket increased from around $245 to $330. Peak inflation years were 2021 to 2023. Prices stabilized slightly after 2024 but stayed high. Our linear regression model predicts inflation of around 2.8 to 3.2% per year. The average basket is expected to reach $360 to $370 by 2028. Western provinces remains slightly above the national average. Overall inflation is persistent but stabilizing. Linear regression is the most reliable model for our dataset. Prices are expected to keep increasing steadily until 2028. We are now ready to integrate this result into our Power BI dashboard. Thank you.